Okay, now what I'm talking about here is just that we can, for any b in the space, there's a linear combination of the vectors that's equal to b, which means that c1 v1 plus dot 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 cn vn equals b always has a solution for c1 through cn. And that's equivalent to saying you can solve this vector equation for x given any b in the space. Okay, well, let's do an example. Okay, the question then is this: is this set of matrices a basis of the space M22, which, remember, consists of 2 by 2 matrices with the usual addition, with matrix addition and with multiplication by scalars, the scalars being real numbers. So a linear combination of these matrices would just be a sum of multiples of these matrices, multiples by real numbers. Okay, so let's test. Okay, now linear independence means this, okay? Linear combinations equal to 0 if and only if C1 through Cn is 0. So we form the linear combination of these matrices, which are the vectors in our space. And we have C1 times the first plus C2 times the second plus C3 times the third plus C4 times the fourth equal to the 0 vector. We want to show that's true if and only if C1 equals C2 equals C3 equals C4 equals 0. And I'll put a question mark on that because we don't know that that's true until we prove it. Well, if we simplify this left-hand side, leaving the right-hand side, excuse me, as it is, C1 times this matrix gives us C1, 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 0. C2 here gives us C2, 0, C2, 0. C3 here gives us C3, 0, 0, C3, and so forth. In the first position, we're going to have a C1, a C2, a C3, and a 0. So when we add these matrices up, our 1, 1 entry to the matrix is going to be C1 plus C2 plus C3. Now you can multiply these out and do the addition yourself and verify that this left-hand side adds up to this. Okay, so what does that tell us? Well, that tells us that this has to equal this, this has to equal this, this has to equal this, this has to equal this. Meaning we have 4 equations in the 4 unknowns, C1 through C4. So C1, well, I'm not going to read it to you. We get this equation, this equal to this equation, this equal to this equal to this, actually gives us C1 plus C2 equals 0. So I kind of messed up there. Because I accidentally wrote down, I'm talking well. I accidentally wrote down C3 here, which should have been C2. C1 plus C2 should be 0. C3 plus 2C4 equal to 0. All my equations are correct except this one. So I'm going to leave it to you to see if these are really linearly independent. But I'm going to go as if this is the correct matrix, which it would be if this was 1, 0, 1, 0. Of course, this is 1, 0, 1, 0. Now I'm not going to get into it. Let's just see what we do if this is the matrix that we came up with. There's an error here. Well, the question then is, can we solve this for C1, C2, C3 such that the C1, C2, C3, and C4 aren't all 0? Because we certainly know if they're all 0, we get a solution. Well, it turns out, and we looked at this last time, that if this matrix is invertible, it follows that all the C1, C2, C3, C4 constants are 0. Why? Well, think about it for a minute and I'll tell you. And if not, if this matrix is not invertible, then you do have a non-trivial solution So it's not linearly independent. So really, all we have to do to establish linear independence is determine whether this matrix is invertible or not. Now, how do you determine whether a matrix is invertible? There are at least a couple of ways. You can row reduce it. First of all, it better be square. If it isn't square, it's not invertible. And it'll turn out that if it isn't square, you don't have a basis for the whole space. But to test whether a matrix is invertible, you just row reduce it. If you end up with a row of zeros, it's not invertible. Okay? Because why? You put the matrix here and augment it with the identity matrix. To get the inverse, you have to be able to reduce this matrix to the identity, and then the identity builds up to the inverse. And you can think about how this works with the elementary matrices and so forth to invoke a little deeper understanding. But the bottom line is, if it row reduces to the identity, it's invertible. If it doesn't, it ain't. Okay? So, matrix is invertible, it turns out if and only if it reduces to the identity. And of course, it reduces to the identity if and only if its determinant is non-zero. And you can think about how the elementary matrices show that, because of course, if it reduces to zero, if it reduces something with a row of zeros, then expand it on that row and you're going to get zero. The determinant is going to be zero. Expand the determinant on the row of zeros. The determinant will be zero. And the determinant of the original matrix is just the product of the determinants of the elementary matrices that you used to reduce the thing times the determinant of the matrix you ended up with. And since the matrix you ended up with has determinant zero, then that means that the original matrix had determinant zero, and you have shown that invertibility, the matrix isn't invertible if the determinant is zero. And there's a little more to it, but that's the idea. So basically, this thing is solvable, as you should know by now, if and only if this matrix is invertible. Okay, solvable for non-trivial, C1 through C4. We can see pretty easily, because we have a column of zeros here, expand on this column. The minor that you get for the 1, 2 element is just the matrix that includes this column, and this column, and you can easily verify that's not zero. Now again, I have the wrong matrix here, so turns out that actually, yeah, okay. I'm still looking to see whether this thing's still a basis, if I do it right. Okay, anyhow, let's not worry about that. Okay, so we take the determinant and we find that the determinant's non-zero, so you can invert this matrix, and the only solution then would be this times the inverse matrix multiplied by the zero vector, and any matrix multiplied by the zero vector is going to give you the zero vector, meaning that the C1 through C4 is the zero vector, meaning the only solutions you have are the trivial solutions, meaning that the set is linearly independent.